Hello, my friends. Got another physics problem for you. So this one, we're dealing with a little bit of integration. We're integrating an acceleration to get a velocity and a position. We're also doing a little bit of relative velocity too, kind of combining these two ideas. So what we've got, I've got a train. It's always a train. The train's moving from left to right in the positive x direction with a velocity of 100 meters per second. And the rocket, which is right here, is about to take off, and it's going to take off with an acceleration vector of 0, comma, a of t squared plus 4. Okay. And I guess this one, that was in the z direction, but it doesn't really make a difference. Okay, so the first part, we want the velocity vector with respect to the ground. Okay, so let's integrate this first. So if we integrate the x, or sorry, not the acceleration. We integrate the acceleration in the x direction with time. This will give us the x velocity for all time. So we are integrating 0 dt. Now this equals a constant. A derivative of a constant is, of course, 0. But we need to fix what this constant is. And what do we know? Well, we know at t equals 0, the velocity in the x direction at 0 is equal to the velocity of the train. Right? At time t equals 0, the rocket has just started taking off, but it's on the train, so it's moving with it. So then this constant equals 100. Evaluate this function, vx of t, at 0. There's no t in here, I just have a constant, but doesn't matter, it still has to equal 100. Okay, so we have our vx. By a similar notion, you will get vy also equals 0. And again, that's because my initial velocity in the y direction is 0. I don't have any acceleration in the y direction, therefore I better be at 0 for all time. And then vz equals the integral of a t squared plus 4 dt equals a t to the third over 3 plus 4t plus some constant. But the velocity of the rocket with respect to the ground starts out with a velocity of 0, so that'll be 0. Okay. So now we have the velocity vector, vx, vy, and vz. So now we just need to integrate one more time. So then x of t equals the integral of 100 dt, which equals 100t plus some constant. But if we evaluate this function at 0, we should get the initial position, which is 0. So this must be 0. Y of t, we're integrating 0 dt. This equals a constant. And it says that the rocket starts off at a height of 4. It starts off 4 meters in the y direction. So this c must be equal to 4. And then I can do z of t equals the interesting one, integral of a t cubed over 3 plus 4t dt equals a t to the fourth over 12 plus 4t squared over 2. And then we would have plus some constant, but we're told it starts off at 0. So I'm just going to write it as 0 and skip a step. And then that's it. I've got my x position for all time, my y position for all time, and my z position for all time. I can put all three of those together in a vector. Or I do them as functions of time. X of t, comma, y of t, comma, z of t. Okay. And notice, so the rocket starts off with acceleration only in the z direction. Okay. So so it has this velocity in the x direction. So this is the only place it's getting any kind of x velocity. So then my x position is of course just 100t. Nothing too surprising there, I don't think. My y position, I start off at 4. My acceleration is 0. I have no acceleration in the y direction. So it just stays 4 forever. And then a similar idea with z, except we know that it starts off with an initial velocity of 0, and it starts off with a position of 0. So that's your answer. We're just integrating an acceleration vector to get a position vector. That's it.